Hey there, science fans! Today, we're diving into the fascinating world of heat exchangers. These incredible devices are like the unsung heroes of the industrial world. They transfer heat between fluids without mixing them, and they're essential for everything from power plants to your refrigerator. Heat exchangers are used in a wide range of industries, including chemical processing, HVAC, power generation, and food processing. In this exploration, we'll break down the different types of heat exchangers, their pros and cons, and how they handle different flow configurations. Get ready to learn about the science of heat transfer. Whether you're a seasoned engineer or just curious about how things work, understanding heat exchangers is key to appreciating the ingenuity behind many modern technologies. So, let's crank up the heat and explore the world of heat exchangers. First up, let's talk about shell and tube heat exchangers. These are the heavy lifters of the heat exchanger world, known for their robustness and ability to handle high pressures. Imagine a bunch of tubes nestled inside a larger cylindrical shell. One fluid flows through the tubes, while the other flows around the outside of the tubes within the shell. Shell and tube exchangers are real workhorses, commonly found in oil refineries, chemical plants, and power generation facilities. They can handle heavy fluids, high temperatures, and high pressures like a champ. However, they can be bulky and prone to fouling, which is the buildup of deposits on the heat transfer surfaces. Next, we have plate heat exchangers, the sleek and efficient cousins of shell and tube exchangers. Picture a stack of thin, corrugated plates with gaskets creating channels between them. Fluids flow through these channels, exchanging heat through the plates. Plate exchangers really shine in applications where space is limited and energy efficiency is crucial. They're commonly used in HVAC systems, food and beverage pasteurization, and pharmaceutical production. They boast high heat transfer rates and are relatively easy to clean. However, they're not the best choice for fluids with large particles or high viscosity, as these can clog the narrow channels. Now, let's explore some specialized heat exchangers designed for specific applications. Air-cooled exchangers use fans to blow air over a network of finned tubes containing the hot fluid. They're a great choice for hot climates or areas where water is scarce, as they don't require a separate cooling fluid. Double pipe exchangers are the simplest type, consisting of one pipe inside another. They're easy to maintain, but not very efficient for large-scale operations. Spiral heat exchangers, on the other hand, are designed to handle viscous or particulate-laden fluids. They excel in applications like wastewater treatment, where fouling is a major concern. Each of these specialized heat exchangers addresses specific challenges and showcases the ingenuity of engineering solutions in diverse industries. From harnessing the power of air cooling to tackling the toughest fluids, these exchangers demonstrate the adaptability of heat transfer technology. Section 5. The importance of flow configuration. Parallel, counterflow, and crossflow. The way fluids flow through a heat exchanger significantly impacts its efficiency. In parallel flow, both fluids travel in the same direction. This configuration is simple, but not very efficient because the temperature difference between the fluids decreases along the flow path. Counterflow, as the name implies, has fluids flowing in opposite directions. This setup maintains a more consistent temperature difference, leading to higher thermal efficiency. Counterflow is commonly used in applications like power plant cooling, where maximizing heat transfer is critical. Finally, we have crossflow, where fluids flow perpendicular to each other. Crossflow offers a good balance between efficiency and compact design. It's often used in air-cooled and plate heat exchangers. Understanding flow configurations is crucial for optimizing heat exchanger performance. The choice of configuration depends on factors like desired efficiency, available space, and the nature of the fluids being handled. Section 6. Maximizing heat transfer. The role of pitch and surface area. Now, let's talk about maximizing heat transfer. The key here is surface area. Think about it. The more surface area there is for heat to transfer across, the more efficient the process will be. This is where pitch comes in. Pitch refers to the spacing between tubes in a shell and tube exchanger, or between plates in a plate exchanger. A smaller pitch means more tubes or plates can be packed into the same space, increasing the surface area available for heat transfer. However, there's a trade-off. While a tighter pitch boosts heat transfer, it can also increase the risk of fouling, especially when dealing with particle-rich fluids. It's a delicate balance between maximizing efficiency and ensuring smooth operation. Section 7. Fouling, the enemy of efficiency. Fouling, the nemesis of every heat exchanger. Fouling is the buildup of unwanted deposits on the heat transfer surfaces, and it's a constant battle in many industrial processes. Think of it like this. Over time, the inside of your water pipes can accumulate mineral deposits that restrict water flow. The same thing can happen inside a heat exchanger, but with potentially more serious consequences. Fouling reduces heat transfer efficiency, forcing systems to work harder and consume more energy. It can also lead to increased pressure drop, corrosion, and even equipment failure. Different types of fouling exist, including scaling, particulate fouling, and biological fouling. Combating fouling is crucial for maintaining the performance and longevity of heat exchangers. Regular cleaning, chemical treatments, and careful material selection are just some of the strategies employed to keep these heat transfer heroes operating at their best. Section 8. Designing for fouling. Strategies for clean heat transfer. So, how do engineers design heat exchangers to minimize fouling? It's all about understanding the nature of the fluids being handled and selecting the right materials and configurations. For example, using smoother tube surfaces can reduce the likelihood of particles sticking and accumulating. In some cases, increasing the fluid velocity can help prevent deposits from settling. Chemical treatments can also be used to inhibit scaling or break down fouling deposits. Regular cleaning is essential, and some heat exchangers are designed for easy disassembly and cleaning. Designing for fouling involves a combination of proactive measures and reactive solutions. By anticipating potential fouling challenges and implementing appropriate strategies, engineers can ensure the long-term efficiency and reliability of heat exchange systems. Section 9. Choosing the right heat exchanger. A balancing act. With so many types of heat exchangers and factors to consider, selecting the right one for a specific application can feel like a daunting task. It's all about finding the right balance between efficiency, cost, space constraints, and the properties of the fluids involved. Factors like heat transfer rate, pressure drop, temperature limitations, and material compatibility all play a crucial role in the decision-making process. For example, if space is limited, a plate heat exchanger might be a better choice than a bulky shell and tube exchanger. Ultimately, choosing the right heat exchanger requires careful consideration of the specific application requirements. Consulting with experienced engineers and heat exchanger manufacturers is essential for making informed decisions that optimize performance and minimize lifecycle costs. Section 10. Conclusion. The future of heat exchange. As we conclude our exploration of heat exchangers, it's clear that these unsung heroes play a vital role in countless industries. From powering our homes to producing the food we eat, heat exchangers are essential for a wide range of processes. As technology advances, we can expect to see even more efficient and innovative heat exchanger designs emerge. Researchers are constantly exploring new materials, flow configurations, and manufacturing techniques to improve heat transfer efficiency and reduce fouling. The future of heat exchange is bright, driven by the need for greater energy efficiency, reduced environmental impact, and enhanced process performance. So, the next time you encounter a heat exchanger, take a moment to appreciate the ingenuity behind these marvels of engineering.